Miguel Eckstein, who was my advisor in graduate school. So so Miguel and I go back a long time, as they'd say. And I remember a peculiar joke that when Miguel has influenced most of my work on foveation, I was very excited for like my first paper coming out and tell Miguel, the foveation revolution one day might be happening, and I hope it does. And Miguel will tell me, well, I've been working. The foveation revolution has been happening for quite some time, Arturo, 25, 30 years before you were born. So without further ado, Miguel Eckstein will be talking about visual search, differences between your brain and deep neural networks. Miguel, el estadio es tuyo. Take it away.
Sure. Thanks everybody who inviting me to participate in this workshop. I've enjoyed the talks this morning and this afternoon. They have been great. Um, some of the work I'll be talking about fits in quite well with some of the previous talks. I will be comparing human performance and some deep neural networks. It will be, for this talk, it will be quite simple. It would be at the behavioral level, it would be at the output level of the DNNs rather than looking at some of the layers and the representations. I sort of put together a talk that has three examples about three examples of differences in which by which humans and actually DNNs search. So there are three examples from visual search. The first two examples sort of are intellectually more interesting. They illustrate different solutions to these problems, possibly reflecting sort of human constraints or different goals that humans might have when they're doing these tasks relative to the more narrow goals that the DNNs have. And the third example is sort of a little bit more obvious, but it has sort of interesting implications sort of in the practical world. It really sort of reveals some of the more obvious limitations of humans when they actually search through images, but it sort of has important implications. So I will start with the two examples. We'll see how we do. I am going to start with a demo, which is a few years old now. You might have seen it. It might also be, it might work not so well over Zoom, but we'll try it anyways. So what I'm going to ask you to do is to just look for a toothbrush, and then you can raise your hand or whatever. You can clap or whatever. Put your little icon there, and then we'll see where we go. So I'm going to put an image up, and you're going to look for you're going to localize a toothbrush. Okay, so, and by now I think most of you probably found the toothbrush, and if it worked, most of you probably found this toothbrush right here, but maybe some of you have missed this one right here, that large one there. And again, it depends on visual angle sometimes, but this is what typically happens. Now, why does it happen? Why, arguably you could actually say that this is actually the large toothbrush is actually way more salient than this small toothbrush. But what happens is when I tell you to look for a toothbrush, your brain rapidly processes the scene, and it's actually sort of attends to sort of spatial scales when you're looking for the toothbrush that are sort of consistent with the rest of the objects and the rest of the scene. And this toothbrush is consistent with that spatial scale for the target, while this one is actually not consistent. It's sort of misscaled, and it would be very unusual to actually have a toothbrush of that size. So it's actually sort of it's an error, but it's sort of a rational strategy because these toothbrushes are just quite uncommon in the real world. So this is sort of the main phenomena, this idea that humans actually miss these giant objects, but the idea is that is actually a useful strategy, because if I actually have other large objects like a big broom or something that might look like a toothbrush, you might be able to discount it just because it's at the wrong scale. So your brain rapidly looks at sort of scales that are consistent with a likely size of the object that you're looking for. So we did this to obviously I wanted to show, we wanted to aside from a demo, have some data. So and of course we wanted to do more than a giant toothbrush. We wanted many objects, and it's actually quite hard to actually have buy some of these giant objects. So what we did is we actually had an experiment that actually used these simpler sort of computer generated scenes where we actually changed the scale of the object so it was consistent with a scene or inconsistent and typically larger, like I just showed you. And we had 40 different scenes. We had different types of targets, and people would actually look at a fixation. Then you would actually have an image that tells you, okay, look for an object, a toothbrush, a cork, or whatever you're looking for. So you just one object per trial, and then the stimulus will come up for a second. So you had time to make eye movements, and then you actually could tell us whether the object was present or absent. So half the times the object was not present, and half the times the object was present. And of those times that when it was present, sometimes it was at the right scale, sometimes it was at the wrong scale. And every single participant just saw that scene with that object once. Okay, so you wouldn't have any sort of learning and so on. And this is sort of the, okay, so this is just an example of the toothbrush at the right scale right here, and that's sort of the sort of a misscale, so it's actually larger than what you'd actually expect. And here are the results. So let's look at what I just showed you for human performance. So this is actually humans at the objects at the normal scale. So this is hit rate. So how many times they actually correctly found that target and said that there was a target present when it was actually at the normal scale. And this is when it's actually misscaled. As you would imagine, yes, if you do this many, many, many times, people will pick up that you're tricking them and they can adjust their strategy. It is not the case that you will miss all giant objects forever. Eventually you pick up that somebody's tricking you and you can adjust your strategy. But this is, our experiments were about 42 trials. So they were quite short and we got a very strong effect. And here's sort of, now what you see these are three different sort of CNNs. And this is actually from 2000. These were the state of the art in 2016. This is a few years back now. And this is the target object probability for the objects that were sort of normally scaled and the misscaled. And what you can see is this dissociation, which is that the CNNs do not have any of this dependence of the relative size of the object, the size of the object relative to the rest of the scenes or the objects around them. So this is sort of the first sort of interesting thing, that these state-of-the-art object detectors are searching for these objects in a drastically different way than humans do. Humans, are really sort of guided by the relative positions and sizes of objects to the rest of the scene, while these object detectors are actually, sort of a little bit more indifferent to that. And of course, this might be changing with time, but this is actually in 2016. I'll show you a slide of another version of this algorithm, YOLO, which is, I think now is up to version 3 or 3.0 or so on. So just as the next slide, I'll show you just a little snippet of we've been interested in this, and we've been interested in trying to find out where actually this happens in the brain. So what we've done is we've put humans in an MRI while we actually change the relative size of an object relative to the rest of the scene, and try to look at the bold activity as a function of that relationship. And we've looked at maybe 7 or 8 areas that were sort of predetermined or pre-segmented. We're using functional localizers. And I'm just showing you one of these areas, TOS, which is an area that actually cares quite a bit about the actual physical size of, is sort of response to physical size of objects, whether the objects are large or small. And here what we see is that this area is actually also caring about the relative size of an object with the rest of the scene. So what you see here in blue is when the object is in its normal size relative to the rest of the scene. And then here, as it's become too small, we're either doing two manipulations. We're either shrinking basically the size of the object itself, so it's too small relative to the rest of the scene, or we are also changing the actual field of view and keeping the retinal size of the object, and those two give you sort of a similar effect. And this perhaps, here the object, and sometimes the object is getting smaller, so this is less surprising, but this is a more surprising thing when you actually make it larger, when you make the object larger in relative size to the rest of the scene, the activity in TOS sort of decreases. And that is not the case for other areas. If I show you sort of FFA or V1, this is not happening. So this is sort of identifying where actually this happens in the brain. And we do similar things. This is years later. So we have YOLO version 3, We do get that when the object gets smaller, we have a significant drop, but we don't get this decrease in activity when the object gets, too large relative to the rest of the scene. So again, sort of highlighting this dissociation in which with which humans and sort of these DNNs are actually processing these scenes. Okay, so now you might be wondering what is it that's behind this dissociation, and we're sort of also, we don't have a full answer, but we're wondering about that too. And there are sort of there are two sort of possible answers. There might be more. So one of is that there's really the current object detectors have sort of processing bottlenecks. As you know, many of the object detectors actually have sort of a bounding box. So they're sort of partitioning and sort of partially analyzing the scene. So they're not really analyzing the entire scene, just mostly having to do with data processing bottlenecks that might, that in the next few years, we might get over. One exception is YOLO. The YOLO algorithm actually uses a sort of a version of the entire image, although it's a little bit low resolution. So it's actually surprising that one doesn't pick up any sort of spatial relationships. So it might be that as these models, and these models are mostly feed forward. So it might be that as actually as we build more things from other domains, and I'm thinking of natural language processing where contextual information is actually fundamental there. Maybe we might start seeing these object detectors show some of the properties that we actually see in sort of human behavior. And sort of the second one is perhaps related to these things from natural language processing. This is just, maybe the object detectors are missing something fundamental and that, and cannot learn these contextual relationships. And this might tie into some of the things that we've seen in other talks having to do with feedback and so on, that might actually allow to a faster and better learning of these contextual relationships. So that is example one. So now I'm going to move to a second example where we see another interesting dissociation between how DNN search and humans do. Okay, here is the task. This is a person search in the wild. What you see are two targets. So there's Ian and Amanda, and just one of them is going to appear in the scene, or neither of them. So it's sort of people are sort of answering a three-class task. Ian, they either say Ian, they say Amanda, or neither. And the way this works is they're fixating here. We're going to eye track them, our subjects, and then the stimuli. And these stimuli are actually videos, so they're going to actually be moving. And these videos were filmed over a period of a month and a half or 2 months on campus at UC Santa Barbara. And Ian and Amanda were instructed to actually dress differently each time. And the people around them and the environments actually also changed. So on. Okay, so, and this is what we're gonna do. Here, what we are interested in is we're interested in understanding which parts of the body, their faces, their heads are contributing to performance for humans and for the CNNs. Which features are important. So we're going to do that two ways. One way is we're going to look at where people are actually looking when they're doing this task, looking at their fixations. And the second way is we're going to manipulate the presence of features in these videos. And I'll show you how that how we did that. Okay, so here is the intact. So these each of these dots is actually a different subject. And of course, it's the same video seen across different trials because they're different people. We're not eye tracking them all simultaneously. I just collapse the data from everybody. And what you can see, and this is what we call the intact condition. I'm going to play it again. And what you see is that people spend a whole lot of time looking at, they look around, but they look a lot of times to the head. Now, this is one condition. In a different condition, we actually eliminated, this is what we call the, there we go, the headless condition. We've eliminated the heads. So their task remains the same. You still have to identify whether Ian, Amanda, or neither are present in the videos. But you've seen lots of different videos, different environments, Ian and Amanda with different clothing, but no heads are present. And what you see is the interesting thing is that people sort of still are looking towards the top part of the body, which we were sort of surprised. They're still looking for that head. Then we have a bodiless condition where the body got eliminated, and this is fairly obvious. They tend to look right there at the head. And then we had a fourth condition, which is, this was hard to do because we had to segment the face and keep the head. It's called the faceless. This is the best we could do, but you can see it's not perfect. So we try to eliminate the face, but you see the hair is there. So part of the hair is there and the head is there. And you can see people are looking at that little empty spot quite a bit. So what we try to do is really combine from all these videos by registering the, scaling the bodies of these people across videos, because they're subtending different angles and they have different sizes, and registering all the fixations into one silhouette. And this is what we got when we did this, sort of a heat map of where were people looking at. Not unsurprisingly, when it's in intact, they're actually looking at right there at the faces. But when it's here we go into bodiless. Well, when there is no body, they're still looking there. There's not really much to look at than there. And then for faceless, even there's no face there, they're still looking there. And now even for headless, it does move somewhere because there is nothing here, but it remains, quite high. So, quite high in the body. They don't really look to a center of mass or anything. They really sort of looking just towards like the neck, where the body finishes, and there that would be the head, but the head is not there. So this sort of gives you this idea that people are actually, focusing in faces and heads, and this is a over practice and pretty common strategy. Okay, when we looked at performance across these four conditions, what we saw is the following. This is performance in the intact, chance is 33%. Now, when you eliminated the face, you had this big drop in performance. And then when you eliminate the head, that was another, that's sort of similar, drop in performance as the face. Now, if you actually eliminate the body, you can see that human performance did not vary much. And there has been literature that people can use body to identify, observers can use bodies to identify people. That's been documented. A lot of those studies are actually people sort of walking by themselves and not less in these more complex, cluttered scenes that I actually had sort of in a search scenario. So this is sort of a little bit surprising. Now, when we ran the CNN, in this case, this is a ResNet 18, where we actually trained the sort of the last layers to actually be able to identify Amanda and Ian. And what we found is that we found a sort of different pattern of results. In particular, we found that the eliminating the face had very little impact on performance for the CNN, and the body was actually quite important. There you can see that detriment in performance, and the head itself, maybe the hair or something, was also important. So here's a second dissociation in which humans and CNNs are actually doing this sort of search task. Humans are very, very face-centered in the way they do this, and they use the body to less of an extent, while the CNNs are actually using the body quite a bit and sort of care less about the face. Now, why would this be? Why would we have this dissociation in sort of strategies? Well, this is sort of what we were thinking. We think, here CNNs is trained to optimize this single task, the search for these people, the Ian or Amanda. But in general, humans in everyday life are really needing to simultaneously optimize a number of different tasks that are important. Identification, but also sort of, the emotional state, sort of inferring what's the emotional state of the person, the gaze orientation, and so on. So what we think is that this might reflect this idea that the human strategy is really optimizing a multiple tasks, while the CN is sort of optimizing one. And the second one is perhaps, there are sort of obviously constraints on human cognitive resources, in particular memory. So as much as we could, we tried to have Ian and Amanda wear different clothes. I do not, like I said, it was over 45 days, the filming. I am sure they repeated the shoes one day or another. So it could be that the CNNs pick up on all these things, while humans, it would be sort of an incredible memory load to pick up all these individual features, even though they're appearing once in a while and they're predictive of somebody's identity. Their humans obviously have memory constraints, and faces are invariant and across at least short periods of time. And so they have a high probability of stability. So that's another reason why humans might actually focus more on faces to do these tasks. So that is the second example that I brought, sort of highlighting how humans and CNN search differently. Okay, so this is I had this summary slide just in case I ran out of time, but I did not. So we're gonna go to the third example. I still have a few minutes. So this one, I'll have you, you will have to pay a little bit of attention because this is a task you might not be so familiar with. So I'm gonna explain what's going on here. What you see to the left, this is actually from medical imaging. This is actually from breast screening, where doctors, radiologists are trying to detect cancer. What you see on the left is the traditional way that breast screening has transcribed for decades. So these are X-ray, 2D X-ray mammograms, and doctors are interested in little features like masses and microcalcifications. Masses are a little bit bigger, microcalcifications are a little tiny. I'll try to show you a simulated one in a sec. To the right is sort of a technology that's sort of become prevalent in the last maybe 5 years or so, 5-6 years. Maybe now, so what you see here, it's called digital breast tomosynthesis. It's sort of it's also X-ray based, but it actually you end up with something like a 3D volume. And what this does, the goal of this is it allows radiologists to better segment the targets they're interested from the normal anatomy. And typically, it actually improves performance. So radiologists do better diagnosing cancer with these 3D breast tomosynthesis images than the 2D mammograms in general. And they're now, I'd say they're actually probably, last time I checked, there were about 40% of the clinics in the US that had this. This is probably now by 70. I need to really check the number. This was a few years ago, but it's sort of like what's now in most clinics coming, or it's there already in the big cities. So we were interested again in how, the relationship between how radiologists look for targets in these 2D mammograms and these 3D images, and the relationship between performance in these two conditions and how it compared to sort of a CNN. And we particularly focused on one task that we thought that is clinically important, which is sort of the detection of these very small targets that are very salient when you look at them, but they're sort of hard to see in the periphery. It's called a microcalcification. Typically, they actually appear in clusters, not by themselves. So this is a little bit of a simplification. So we sort of inserted these. This is a collaboration with the University of Pennsylvania and the Santa Barbara's Women's Imaging Center. We stuck this at random locations in these phantoms. These are not actual DBTs. These are actually phantoms created by Penn. So complicated phantoms. They look similar. They're not exactly what real DBTs, but they look similar to those. And there are about 100 slices. I'm just showing 4 in the 3D. And we stuck this at a random location. And we also put it at a random location in the 2D. And then the humans and the radiologists and the CNN had to search for that little target. And when you actually do that and you measure CNN, this is actually a CNN that's actually specific unit. It's specific for medical images. That sort of, it was 2016 was sort of the state of the art in image segmentation for medical images, and we trained the last layers to do our task. And you can see that it does better in the 3D than in the 2D, which is actually consistent with sort of this notion that the 3D, because it has volumetric information, carries more information than the 2D image. But when we actually looked at our radiologists, look what happened. We had this incredible dissociation where radiologists did much poorly for this particular target that I just showed you, and in the 3D than in the 2D. And so this is actually an interesting result. Because there's a big dissociation, but if you're not a vision scientist, if somebody in medical imaging or radiology, you might think this is actually sort of, oh, what does this happen? But those of you in the audience, you're a vision scientist, so you probably have figured out what's going on. What happens is this target is extremely salient when you foveate it, and the 2D image you can actually rapidly, but with moderate time, you can actually scan the image and actually find it. But in this huge volume of 100 slices, if you count the typical clinical times of about 2 to 4 minutes, radiologists do not have the time to scrutinize every slice and every spot of every slice. So they often miss it. So here's an example I actually show you. So what you're seeing here, just before I'll pause it for a sec, in green are the fixations of the radiologist. And at some point, you're going to see a little white ring that's going to appear for a few slices, and that's where the target is going to be. And you're going to see how they miss it. So they're scanning around, they're fixating here, there, that's it, right there. I don't know if everybody saw it. It was right there. I'll put it back. There we go. So right, you're going to see here, right there, maybe I missed it. Okay. There you go. That's where the target is. It's hard to see, but if you're looking away, it's going to be very easy to miss. So clearly, the what explains this association is really that the humans have this foveated visual system, and they're under exploring this 3D volume, which leads to this dissociation with CNNs, which are non-foveated, and actually thoroughly exploring the entire 3D volume. Okay, so to summarize, I gave you sort of 3 examples, very different examples of how humans and CNNs search in different ways. The first examples emphasizes how the human brain heavily relies on contextual relations for object search, while current CNNs, and like I said, I haven't tested, this could have changed. Maybe if you have a pointer towards one CNN we need to try to see if it has these properties, that'd be awesome. But the ones we had tested till recently do not seem to incorporate such relationships. The second one was really visual search of a person in the wild, and sort of illustrated how the human brain adopts strategies that optimize performance across a battery of tasks, rather than CNNs are trained to do these narrow tasks. And that might explain sort of the difference in strategy. And then the third one was sort of identified in a practical domain instances that reveal sort of visual cognitive bottlenecks in humans that result in these large search errors for these small signals, and it sort of suggests that those might be good circumstances where AI might greatly help mitigate human errors. And that was presented in cancer screening by radiologists. So with that, thank you very much.